We're good to go. Hello, everyone. I'm Zackory Erickson. As noted, I'm an assistant professor in the Robotics Institute at Carnegie Mellon University, where I lead the Robotic Caregiving and Human Interaction Lab. And today I'd like to share with you some of our work on developing capacitive servoing for physically assistive robotics. So my group's research focuses predominantly on intelligent physical human-robot interaction, where robots are in close physical contact with people. These are robots that are touching a person, applying force, sensing, and manipulating both the human body and objects around the body. And my group's research has applications in healthcare towards the development of robotic caregivers that can assist people who require daily care and physical assistance with activities of daily living. Now, in order to get robots physically interacting with people, it's crucial for a robot to be able to sense where a person's body is and track human motion in real time, whether that be tracking a person's face during feeding assistance, sensing or adapting to limb motion during dressing assistance, or navigating the contours of the human body during bathing and hygiene assistance. And there's been a couple of different methods that robots have used in order to sense human pose in the past. One of the most common approaches that probably you're all familiar with and you think of first is visual perception, such as with a camera. You might be, for example, familiar with tools like open pose. However, things like the robot's own body and different objects like fabric garments can all visually occlude sight of a person, and I'll show that in a second. Another method that's been used is force perception, where a robot is using its sense of touch or force torque sensors in order to estimate a human pose, but this requires robots to be continuously making contact with and applying force onto people in order to directly sense them. And more recently, my colleagues in other research groups have demonstrated how robots can use pressure mats either on a bed or on a floor to estimate a person's pose, yet such approaches, they struggle with estimating local pose details or even tracking real-time human motion. But I really want to emphasize, why can't we just use a camera on a robot? It seems like the most intuitive thing to try first. And to be honest, vision does work in many cases, but it turns out that there's a lot of scenarios in physical interaction where substantial parts of the human body become visually occluded. In this case right here, about halfway through this dressing scenario, the robot can no longer see a person's body. Not only is the robot's own arm kind of getting in the way of its cameras, which are mounted on its head, but this fabric garment is also visually occluding sight of a person. And this lack of vision is one of the major challenges that capacitive sensing aims to address. In fact, in this video, the robot is using capacitive servoing to adapt to any arm movements made by this participant. So what I'd like to share with you today is how we've developed new capacitive sensors that can be used to accurately sense local human pose near a robot's end effector. We use learning to build pose estimation models from capacitance data or data from a capacitive sensor. And then we evaluate through human studies how robots can use this sensor to perform servoing around the human body and adapt to human motion during physical assistance. But first, what is a capacitive sensor and how does it work? Well, you might be familiar with the classic physics definition of a parallel plate capacitor, where we have, in this case, two parallel conductive plates. One of them is a sensor, the other one acts as a ground. And given this setup, we can use a common capacitance equation to determine the distance between these two conductive plates. We have some constants, K, which is a dielectric constant, epsilon naught, which is a permittivity of space, as well as a surface area and a capacitance measurement from the sensor. And it turns out we can use this exact same approach to sense the human body. We again have a conductive sensing plate, but now the ground becomes the human body. And we can use similar techniques and equations in order to determine the distance to a person's body. And in fact, you're probably very familiar with capacitive sensing. You probably use it every single day yourself. Touchscreens on consumer devices use capacitive sensing to detect when we make contact with the screen. Capacitive sensors are common within consumer devices, such as touchscreens, virtual reality controllers, and a lot of different wearables. Within human-robot interaction, capacitive sensors have frequently been used as a form of proximity sensing in many cases, to avoid collisions with people and various objects in an environment. Prior research has also shown how capacitive sensing can be used during object manipulation, enabling a robot to perform servoing around stationary objects or to pre-shape an object grasp. Yet in comparison to prior work, we explore capacitive sensing for physical robotic assistance, including servoing around the contours of human limbs and tracking human limb motion in real time. So when compared to other pose estimation approaches, capacitive sensing offers robots a number of benefits. One, it allows robots to sense through some visually opaque materials such as clothing and wet cloth. It doesn't require robots to make contact with people in order to sense them. And lastly, it allows robots to track human motion in real time. So in order to start, we've developed a single-axis capacitive sensor, which could be either held by or mounted to a robot's end effector, which is shown here in this figure on the left. And then we explored how a robot could use this sensor to estimate the vertical distance to a person's body in real time while providing assistance. So with this sensor, we collected data from a single human participant as a peer 2 moved this capacitive sensor downwards towards a person's hand. And what we can do, given all the measurements from this process, we can plot all of them, kind of shown here, distance versus capacitance. And in order to estimate distance from a capacitance measurement, we used a nonlinear least squares optimization to fit a function to this data. And this is a function inspired by the capacitance equation for a parallel plate capacitor. And so what this does is it gives us a very simple and fast function for estimating the vertical distance from a robot's end effector to a person's limb. We then conducted a study with 10 able-bodied participants in which the robot used this capacitive sensing technique to sense and adapt to the vertical arm motions made by participants while dressing on 2 different garments, both a hospital gown and, in this case, in this video shown here, a long sleeve sweater. And this works even if participants are wearing other non-conductive, long sleeve, non-conductive cotton clothing garment here. So despite this unscripted human motion, the robot's end effector is able to stay approximately 5 centimeters above each participant's arm. And capacitive sensing is allowing a robot to track this human motion in real time, regardless of visual occlusions, and they're able to sense the human body through cotton cloth. But another neat aspect of this approach is that it allows a robot to follow along the contours of a person's body. So if we ask participants to hold their arms out and hold steady, the robot can traverse a path along the surface of their limb. So this blue line here and the shading represents or illustrates the mean and standard deviation of the robot's movement from our trials, where a robot's end effector is trying to stay 5 centimeters above each participant's arm. And in more recent work, we've demonstrated this capacitive sensing technique for providing dressing assistance to individuals with physical disabilities. This same model, optimized for a single able-bodied participant, generalized to people with disabilities. In this case here, the robot is using a capacitive sensor to adapt dressing trajectories that it has learned in simulation. And capacitive sensing is allowing the robot to adapt to this involuntary vertical motion made by this participant with cerebral palsy while dressing both sleeves of a hospital gown. So this participant is exhibiting some involuntary motion. It's just part of their condition with cerebral palsy. And the robot is able to sense that and adapt accordingly so the participant isn't slapping their arm into the robot over and over again. But there is a limitation here. This single axis sensor is only able to sense vertical distance away from a person's limb. It's not able to sense other types of distances or motions, such as this lateral distance, where the arm is no longer directly underneath the sensor, nor can this approach sense the orientation of a person's limb in space. So how can we estimate this kind of human motion during physical HRI? So we do this by developing a multi-dimensional capacitive sensor. This sensor consists of a 3x2 grid of copper capacitive electrodes connected to a microcontroller board. And these electrodes, they emit an electric field, which in turn allows a robot to sense conductive objects like the human body. And now with this multi-electrode capacitive sensor, The robot is able to sense the human body from about 10 to 15 centimeters away. We can sample capacitance measurements at frequencies over 100 hertz. And yet, most importantly, we're able to sense this four-dimensional relative position and orientation of a human limb. But what do I mean by sensing four-dimensional pose? So here's a PR2 robot again. And in the center is that capacitive sensor. And if we zoom in, what we're going to be looking at is a point on the person's limb that's closest to the center of the capacitive sensor. So given this point, let's look at what is this relative pose that a robot is sensing? What are these four dimensions? The first two are going to be this lateral and vertical distance between the capacitive sensor and the highest nearby point on the person's limb. The third dimension is this pitch orientation between the sensor and an axis running along the surface of a person's limb. And lastly is the yaw orientation between the sensor and the central axis of the limb. And together, this represents the four-dimensional pose of a person's limb that the robot is going to be sensing. And for those of you who might recognize this isn't 6 dimensions, there's a reason for why. It's simply due to the ambiguity along the central axis of a cylindrically shaped limb. So if you imagine the human arm as a cylinder, it's very difficult to sense rotation around that cylinder as well as movement along the central axis of that cylinder. So in order for a robot to perform capacitive servoing around the human body, we start by collecting time-varying capacitance measurements from a single human participant as the PR2 is moving this capacitive sensor on both the person's arm and leg. And we can feed all this data in and train a fully connected feed-forward neural network, which takes as input a window of prior capacitance measurements and outputs an estimated pose of the person's limb. Again, note that this model is trained on capacitance data from only a single human participant. And in order to control a robot to perform servoing around the human body, we use a PD controller to update the robot's target end effector pose. Now, this is a fairly straightforward controller, so I'm not going to really dive into the details of how it works, but one of the benefits I will note of using a capacitive sensor is that it enables a robot to perform complex assistive tasks like helping someone get dressed or cleaning off their body with very simple control algorithms. We then set up a study with 12 able-bodied participants to evaluate sensing ranges, generalization, and servoing using our 6-electrode capacitive sensor, which is mounted onto a PR2's end effector. And we began by characterizing the sensing ranges of the capacitive sensor and trained pose estimator. So to do this, we computed pose estimation error as the PR2 moved the capacitive sensor away from each participant's stationary arm. These motions are shown in the video on the left. And if we look at all of these motions, they generate this semicircular planar region, which is now shown on the left figure. And this is just demonstrating all of the possible end effector positions. And all these different positions, when we capture measurements from the capacitive sensor at these different positions and feed them through our pose estimator, that results in an error plot, which is shown on the right. And here, dark blue is low estimation error, whereas green is high error from our trained pose estimator. And the capacitive sensor is working best when the center of the sensor is at most 15 centimeters from the arm, where the mean pose estimation error is about 1.5 centimeters within this region. And we similarly characterize rotational sensing ranges and observe that the capacitive sensing approach is most accurate when the sensor is oriented at most 30 degrees from the human limb. So as discussed a few slides ago, and I've been kind of emphasizing this, is that we trained our pose estimation model on capacitance data from only a single human participant. Now, in order to evaluate this model, we then repeated this training data collection process with all 12 participants. And this essentially forms a test set for us. And when we computed the pose estimation error of our model averaged over all 12 participants for each of the 4 sensing axes, we show the results here in this table above. And although our pose estimation model was trained on capacitance data from only a single participant, the model exhibited on average less than 2.5 centimeters of position estimation error and less than 10 degrees of orientation error per axis. We also investigate the benefit of training capacitive pose estimation models on data from more than one human participant. And we do so using a technique called leave one participant out cross-validation. So how this works is we retrain our pose estimation network on capacitance measurements from 11 participants and compute the pose estimation error on data from a single held out participant. We then repeat this process by holding out each of the participants, and the table above shows the average error from all 12 training and test sets. But the main takeaway here is that the two tables we just saw are actually quite similar. Regardless of whether we train capacitance data on a single person or on 11 people, we observed very similar pose estimation performance with less than half a centimeter of difference in position estimation error and less than 1 degree of difference in rotation estimation error. And these results indicate that pose estimation models trained on capacitance measurements from one participant may generalize to a larger population of people. As a part of this work, we also presented a servoing algorithm for a robot to control its end effector both proximally and distally along a human limb using a capacitive sensor, as shown in the video on the left. And throughout our trials with participants, capacitive servoing was able to keep its end effector, it was able to keep the robot's end effector on average within 1 centimeter from the target distance away from the human arm, while simultaneously traversing a path along the arm around a bent elbow. We also evaluated the case where a robot navigates along a human leg. Again, capacitive servoing kept the robot's end effector on average within 1 centimeter from a target distance away from the top of a human leg, and it enabled the robot's end effector to traverse from the thigh to the ankle around a bent knee. Now, we also conducted a separate study with 4 able-bodied participants in which we demonstrated that capacitive servoing can be used by a robot to provide assistance for 2 different activities of daily living. Now, the first one we've already seen before, dressing, pulling on the sleeve of a hospital gown onto a person's arm. But now this second task is going to be bathing assistance, in which the robot is using a wet washcloth in order to clean off a person's arm or leg. So when providing dressing assistance, we observed that the robot was able to use capacitive servoing to sense and adapt to human motion, such as these lateral arm movements and rotations that we see here in this figure, where participants are asked pretty much in an unscripted manner, just move your arm around, extend it outwards, bend your elbow, lift your arm up and down, and robots are able to sense that accordingly. And in the next part of our experiments, we assessed how a robot is able to use this same approach to assist with this other task, bathing. Here, the robot is using capacitive servoing along with this wet washcloth in order to navigate and clean off the surface of a person's leg. And here, the robot is in this capacitive sensor, it's able to sense the human leg through this wet cloth, and it does work well in many cases, but it's not perfect. Sensing the human limb through wet cloth is a bit more challenging with a capacitive sensor. And here's an example in which the robot failed to fully clean off the leg when it briefly lost track of the leg near the knee. And this resulted in it missing, as you can see here, kind of visually, it missed some of this blue powder that was placed near the knee. And so it worked in most cases, but it doesn't always work. And definitely sensing capacitive signals are impacted by objects and materials that are especially highly conductive, and wet cloth is definitely not an exception there. And similarly, we also looked at bathing assistance along a human limb. Despite this model, this pose estimation model, being trained on only a single human participant, and with very limited training data, all the data was collected in the real world, capacitive servoing was still able to generalize across multiple people with variant sized limbs and generalize across both arms and legs. And so all of this kind of sensing modality, it's ultimately working towards the development of intelligent robotic caregivers in healthcare. My goal here is really bringing robotic caregivers into real environments to assist and interact with real people who require daily care and physical assistance with activities of daily living. So overall, capacitive servoing, it's a new technique that enables robots to both navigate along the body and track human motion in real time. We've developed new capacitive sensors for robots to accurately sense the human body. We've trained pose estimation models on capacitance based on capacitance data. And then we've performed evaluation through human studies in which we found that this servoing approach generalizes well across people for multiple physical assistance tasks. And so with that, I'd like to thank you all, and I'm happy to take any questions.
Wonderful. Questions from the audience? Yeah, go for it.
Next presentation, Zach, I have a question for the wiping or the cleaning task. So
Yeah.
compared to a force torque sensor, so what's the pros and cons of using the capacitive sensor?
This is a great question. So I actually believe that for something like bathing, you can probably do pretty well with a force torque sensor. And I myself haven't used force torque sensor in this context, but during my PhD, our research group had done this in the past using force torque sensing. So I would say in many cases, it's definitely possible, and it can work in some cases, especially if you're using a 6-axis force torque sensor where you can, sense maybe if you're starting to slip. I'm not sure if this is actually, if you can see my camera, but essentially if you're slipping off of the arm, essentially the forces and torques there might be able to tell you that you're kind of applying force now at an angle rather than, head on at like a normal force. And that might give enough signal for the robot to, maybe readapt. In comparison, though, I think sort of capacitive sensing gives you, in many cases, that same information, particularly when you use an array of these capacitive electrodes. If you start to deviate, from the central axis of a human limb, the robot can sense that accordingly and move its end effector back onto the limb. Particularly, one of the things I think might be really difficult for a force torque sensor is around joints. So when you want to have a robot bend around an elbow or bend around a knee, moving along a joint with just a force torque sensor is a bit tricky, especially if there isn't just like, if a single approach of, just move downward, if I don't feel any force, if that doesn't work, then it's a little bit more tricky. Then you need to bring in other sensing modalities, like, using vision with, an estimated human pose in order to follow along a limb. And that's where I think kind of capacitive sensing comes in as an extra benefit, is that it can sense things like it can sense a bend in an elbow and have the robot navigate around an elbow. Again, using very simple control algorithms and doing this kind of all as a feedback control loop. So I would say that's probably the biggest difference that I can note. I will say you're right. You can definitely do it with force torque sensing, but I think there's some cases, particularly joints, where capacitive sensing does give it a little bit of an advantage. But if you're using other modalities, vision, capacitive sensing, force torque sensing, all combined, I would imagine that's probably the best that you could, really do. Great question.
Any other questions?
When you were measuring the air in pose estimation, do you have an idea of where most of that comes from? Is it sensor noise or the difference in physical structure of the body?
The belief is it's primarily due to, let me see if I can go back a slide so everyone can kind of see where we're referring. So this will work. So so a lot of this error, I guess it partially depends. If we're referring to why does error happen, when the sensor gets further away, that's just merely due to how capacitive sensors work in general. Due to electric fields, they're more of a local sensing or short range sensing approach. So as you get further away, of course, you get less signal, and there's just more noise, or essentially more of your signal dissipates as it gets further away from the sensor. Now, if we're talking about, why is there, error, even if we look here, kind of why is there in this region 1.5 centimeters of error, or even in, I think another slide I also show some other error plots. So these, I'm almost positive it's due to variation in human limb, just different body sizes. And we train our model on, well, in this case, we evaluate, it's trained on a single human participant. And so the model has really only seen, one circumference of human limbs. And actually the model is trained on both arms and legs. So it's given, large thighs and very thin wrists, and it sees capacitance measurements from all of these. But there isn't currently a prior into the model of what is the surface area or circumference of the limb that you're nearby, right? So, and one of the reasons why this matters is that if you have this capacitive sensor and you put it, 5 centimeters away from a person's wrist, which is, much smaller in circumference, and then you put that same sensor near a person's thigh, 5 centimeters away from a person's thigh, which is much larger, you will actually get larger capacitance readings or measurements from when it's close to the thigh. And that's simply because, if you can recall all the way back, the capacitance data, this distance equation from a sensor to some conductive object is dependent on the surface area. And what that means is that when you have a larger surface area of an object, you get a larger capacitance measurement. And we're not feeding that information into our pose estimation model. So that's pretty much, our model is just kind of having to kind of guess the surface area, I guess, in some way you could kind of guess, or, take an average. And so that's why my belief is most of this error is coming from. And I think probably a solution to this is to use visual information to give a capacitive model at least some prior in terms of, what is an approximate circumference of the human limb near the model, to get rid of a lot of this error. So it knows that, 5 centimeters, this is the type, if I want to be 5 centimeters away from, this size of a limb, this is the type of measurement, that I should be expecting. Great question.
Wonderful. I believe there's one more. 7, go for it.
Yeah, I had a question about the generalization. I'm wondering whether how the error changes if you say trained on a right hand and we're testing on a left hand, or whether you had any of your 12 participants being right or left-handed mostly.
Say this again, right hand versus left-handed?
Yeah.
Could you elaborate?
Yeah, sorry. So for my question is how the generalization for the pose estimation. Yep. So I'm guessing you trained probably on the right hand when you were doing the pose estimation. But
yes,
yeah.
Yeah. So this only happened with this single. So this is a good question. I'll preface this by saying we only did this with this single capacitive sensor. When we switched over to this array of electrodes, we actually had a different approach for capturing data, and that looked like this. So we moved over a wrist, but also their forearm, their upper arm, and then also we collected measurements around their leg. So just as a preface, the question of moving towards a person's hand might only be relevant towards for this paper. But in terms of generalization across, say, the right hand versus left hand, it's maybe an open question, although I wouldn't assume there to be much difference under the assumption that people are fairly symmetrical, left versus right side of their body. I think if data from this were to differ, if the capacitance data from captured above a left hand versus above the right hand, if it were to differ, it might be due to asymmetry between the parts of the body. Maybe if you have a much larger right hand than a left hand, or I guess alternatively, if the data collection process had errors, from a robot's perspective, then there might be some different measurements there. Not sure if this is really getting what you're wanting, though.
No, it does answer part of my question. Thank you so much.
Okay, absolutely.
Well, with the interest of time, I need to wrap this up. But Zackory, that was a wonderful presentation. That gave me a lot.
Thank you.
Think about, look follow up later. But with that, let's thank our speaker again.